Welcome back to Business Analytics for Decision Makers. In this lesson, we're going to cover queue modeling basics. Last time we introduced queues, and we learned that variation in service and arrival rates were the cause of queues. We model queues to determine the service level that minimizes our cost. And so what we saw was the cost of operating a service facility was composed of two components: service costs, which were driven by the number of servers we hired and was linear, and the waiting cost of our customers, which was nonlinear. The summation of these two provided our total expected cost for a firm, and we wanted to find that point that minimized it, which was the optimal service level. In order for us to develop our analytic model of a queue, we needed three things: the arrival rate, how fast our customers are showing up; the service rate, how fast a server can handle our customers; and then the third thing was the number of servers. So how many people or machines are there to process our customers? In this lesson, we've got 6 objectives. The first is to cover the most common arrival distribution for our analytic model. The second is to look at the most common service distribution for our queuing model. Then we're going to go over Kendall's notation, which is our common way to describe a queuing model. And then we're going to talk about some other arrival and service distributions that can be handled by analytic models. And once we've done that, we're going to go into the queue assumptions. What are some of the assumptions of our analytic model that we need to look out that they're not being violated? And then finally, we're going to look at the metrics of queue performance. And so this will be introduced with some math that's driving the models, but more importantly is to understand, what do these numbers mean? How do we interpret them? So let's launch into the lesson. What's the most common arrival distribution? Well, that's the Poisson distribution. And what a Poisson distribution gives us is, with an average arrival rate, which we display by the symbol lambda, the probability a certain number of customers x arrive in a given time window. And so mathematically, the probability of x is e to the negative lambda, lambda the x, all divided by x factorial. Maybe not the most useful, but visually, what does this look like? So if my lambda equals 1, you can see the probability of 0 customers is about 37%. The probability of 1 customer is about 37%. The probability of 2 customers is about 18%. 3 customers, 6%. 4 customers, a low number. And then 5 even lower, and so on and so forth, right? But there's a chance that you can have 8 or 9 or 10 customers show up in a given time period with a lambda equals 1. Now with lambda equals 2, you see this whole distribution shift to the right. And with lambda equals 4, you'd see it moving even further right, where 4 is the most probable number that will arrive in a given time period, but the probability of 5, 6, 7, 8, or 9 is also likely. One of the things to note is that the Poisson distributions are discrete. And so what this is saying is, within a minute, I'm only going to have 3 customers show up, or 2 customers show up. It's impossible for 2.2 customers to show up in a specific time window. The most common service distribution is the exponential distribution. And an exponential distribution requires this average service time mu. And it gives us the probability service will exceed a specific time, t. So the probability of t is equal to e to the negative mu t. What does this look like? And so if mu equals 0.5, we'd have this downward sloping curve. So the probability that you're done before you even show up is 1, right? It's never going to happen. And then it descends. Now, if mu then equals 1, you see it shift, and if mu equals 2, it shifts more, right? So you're likely to be handled faster. So if I can handle 2 customers in a given time period, I'm obviously going to be twice as fast as if I can only handle 1. One of the things to note is the means. And you can see the mean is actually 1 over mu of the distributions. The other thing to note is that the exponential distribution is continuous. So I can help a customer in 42.2 seconds. Similarly, I can help a customer in 42 hours, 13 minutes, 42.7 seconds. And so it can take on any feasible time range, and so any number is possible. What maybe is more difficult to see is that the Poisson and exponential are actually linked distributions, where the Poisson is the discrete case of the exponential. And so they both fall into this Markovian family, which we'll see more of later. Kendall's notation is the common way by which analytic cues are described. So it's good to understand exactly what these numbers are going to mean. And so the first element of Kendall's notation is A. And what A tells us is what the probability distribution is for our model. If it's a Poisson distribution, which is the most common, it's M because it's in the Markovian family, so it'd be M. The second element, B, is the service time distribution. So in this case, an M would mean that it's exponential. Once we've got our arrival in service, the third element we need to model Qs is S, right? The number of servers. So with these three things, we have enough information we can model any Q. The fourth and fifth elements of Kendall's notation are optional. And so the fourth element is also an M. And what this is the maximum queue length. And so if our queue can only handle 4 people, the analytic models are able to handle that. So store capacity, for example, would be why we need to limit our queue length. If it's not shown, it's assumed to be infinity. Now our fifth element is P, and P is the population size. So if I'm modeling aircraft and I only have 20 aircraft, if 3 of them are awaiting maintenance and 1 is in maintenance, my arrival rate is going to change because now I'm only flying 16 aircraft, so only those 16 are possibly going to come in. And so our analytic models can be adapted to handle small population sizes. Again, if it's not shown, it's assumed to be infinity. So let's do some practice because we're going to shortly just see numbers to describe queues as opposed to pictures. And so let's say that you have Poisson arrivals, exponential service, and 1 server. What does this look like? Well, it looks like a line going into a single server. And so in Kendall's notation, we would describe this as an MM1. Now what if I had 3 lines with Poisson arrivals, exponential service, and each one was being helped by 1 server? So I've got 3 lines in front of a server. So each line has its own server. In Kendall's notation, how would we model this? Well, it would be 3 MM1s. Now if I have Poisson arrivals, exponential service, and 3 servers, right? What would this look like? Well, it'd be a single line, and then 3 servers are helping that line, right? So it'd be like Chick-fil-A. In Kendall's notation, this would be an MM3. So our fourth one, Poisson arrivals, exponential service with 3 servers, a max queue length of 4, and a population of 20. So we're going to use all 5 of those Kendall's element pieces to describe it. So what does this look like? I've got a max line length of 4 and 2 servers and a small population, so at MM3, 4, 20. Now our fifth one, what if I have 2 lines with Poisson arrivals, exponential service, and each line is being helped by 2 servers? So this is almost like TSA. But now let's throw in a hitch, and our population is limited to being only 100 people. So maybe TSA at a small airport. So what does it look like? So it looks like this. And how would we describe it in Kendall's notation? Well, it'd be 2 MM2s, infinity, and then 100. Since we have the 5th element, we have a limited population size, we also have to include the 4th element of Kendall's notation, which is saying our queue length is not restricted, so that infinity needs to be shown. So what are other arrival and service distributions our model can cover? Deterministic models is one that's common, and in these models, what if I could schedule my arrival, or if I'm being provided service by a machine process, so it takes an exact amount of time every single time, and that's deterministic. Alternatively, there's general, and general distributions are any distribution with a mean and variance. So normal distributions or gamma distributions can also be modeled by our analytic models. So what are the assumptions of our analytic queuing model? One of the first is that the model's FIFO. The first customer in is also going to be the first customer out. And what I mean by this is if we have a line of customers and I'm done with the customer that was presently being helped, if someone shows up in line, they don't get to just jump to the front of the line, right? They have to go to the back of the line, and the line moves forward in progression. So it doesn't seem like a strong assumption there. Our second assumption is that there's no bulking or reneging in the analytic model. So no matter how long the line gets, people aren't just going to walk away. Our third assumption is that arrivals are independent. And I'm sure we've all been out at a restaurant and you've seen a bus pull up that you've wanted to race because you know all of a sudden a whole bunch of people are going to come out of that bus and they aren't arriving independently of each other. Again, this maybe isn't a strong assumption because the possibility is pretty well encompassed with our Poisson arrivals of fluke events like this occurring. Our fourth assumption is that service times are independent. And so there's some behavioral studies saying that if the line's short, the productivity of your server might alter, right? They might work quickly if they're trying to get to lunch, but it might slow down if that line gets a little longer and they realize, hey, I'm going to be stuck here for a really long time. And then if they see a line that just stretches out of sight, they might slow down further because they realize they're going to be busy for the rest of their day. Our fifth assumption is that service systems operate under steady ongoing conditions. So our arrival and our service rates remain the same throughout the day, right? So if our coffee shop, what we're saying is the number of people that want coffee in the morning is going to be the same at noontime, and it's going to be the same after dark. So that could be a strong assumption. Otherwise, we have to model our queue model just for specific time windows in which the service system is steady state. Now, let's talk about queue performance. The first thing that we often care about is average server utilization. And what that is how often am I helping customers, my servers are helping customers, versus how often are they idle, just sitting around having a cup of coffee. And so that's server utilization. The next thing I might want to know is what is the average number of customers in the queue? So how many people on average are waiting in line to get help? The next thing I might want to know is the average number of customers in the system. So this includes everyone in the queue as well as all of those customers that are also being served. I also might want to know the average time a customer spends waiting in line. And this is from when they first, and this is designated WQ, and this is when a customer first arrives all the way until they step up to receive service. Analogous to this is the average time a customer spends in the entire system, which is W. And so this is from when a customer first arrives all the way to when they exit the system and move on. They're done with the process. Other things I care about is what is the probability of 0 customers? And this is really just how often is my server just sitting around having that cup of coffee. 1 minus rho, average server utilization, essentially. And then what are the probability of n customers in the system? So maybe I want to know if there's 3 or 4 or 5 or 6. And so in this case, the probability of exactly 5 customers in the system maybe is 20% of the time. And so those are our queue performance metrics that we're going to look at. How do these adapt if I go from having 1 server to S number of servers? You can see there's not too big of changes. So what are our queue restrictions? Well, there's one major restriction, and that is the arrival rate lambda must be less than the service rate mu, or the system blows up. So if I can't provide service to my customers faster than they're arriving, the line's just going to grow and grow and grow and grow to infinity. So we can collect all sorts of information about queue performance, but how does this relate to cost? Well, total cost is equal to the wait cost plus the service costs, as we discussed last lesson. And wait cost we can express mathematically as C sub W times L, where C sub W is the customer waiting cost per unit of time, and L is the average number of customers in the system. Service cost we can express as C sub S times S, where C sub S is the cost of service per unit of time, and S is simply the number of servers we have. So the type of business will determine whether waiting cost is based on customers in the queue, which is L sub Q, or in the system L. So typically if they're employees of your system, you would use L because it's an opportunity cost, whether they're in line or they're being served. They could be doing something else. If you're providing service and they're non-employees, then you typically use L sub Q because the cost is only that time prior to them getting service where they may be able to walk away or get upset. So our standard business decision choice is S, and S in return affects L. So it'll affect both our service and our waiting costs. A less standard but common decision also that businesses have to analyze using these models is we want to evaluate a change in service rate. So what if I could pay for more effective service? This in turn will raise the cost of service, but it'll also affect L, the length of that line, because I'm able to process my customers faster when they arrive. So to review our lesson objectives, our most common arrival distribution is the Poisson distribution, a discrete Markovian distribution. Our most common service distribution is the exponential, which is the continuous version of the Poisson and the Markovian distribution family. And then we covered Kendall's notation and its 5 different elements. And then we talked about how these analytic models are adaptable to cover both discrete distributions, so machine processes or scheduled arrivals, as well as more general distributions. So if what you analyze when you go out and field data is a normal distribution or a gamma distribution, the analytic model can be adapted. So some Q assumptions. We covered those as well to look for if they're strongly violated, you might get results that are funny. And then we talked about Q performance and how it relates to our cost decision, ultimately why these models are typically being run. So our next lesson, we're going to cover Excel. So I'm going to introduce queuing templates to you. And we're going to look at the inputs where we put them into our model, our outputs of the model where we read these out, and then how we're going to make decisions using the model. So I look forward to seeing you next time. Have a great day.